The last section of chapter 6 is taking now our Lewis structures and actually showing how the bonds occur. So sometimes people like to know this information before they draw the Lewis structures. Sometimes it confuses them by the more detailed drawings. But anyway, we're going to be drawing both covalent and ionic bonds. So you need to know that covalent bonds share electrons. We'll be representing the sharing of electrons by circling the dots or the electrons that will be shared. And once again, we're only going to be drawing the valence electron number of electrons using the electron dot structure. So in this chemical reaction, we have an oxygen combining with another oxygen and yielding or producing O2, two oxygens bonded together. So let's begin by drawing each oxygen with its valence electron number. Let me switch to black ink. So each oxygen is going to have 6 dots because it's in group 16. So 2 sides with 2 dots each and 2 sides with 1 dot each. Remember, it doesn't have to look exactly like mine, but you do want to format this in such a way that the single lonely dots can pair up with other lonely dots. So I have this. I am then going to use a different color ink for you to show you the bonding by circling. So this dot will share and bond with this dot. And the same thing here. They will overlap their outer shells. And then I'm going to draw a new finalized bonding that is occurring. So I'm going to draw both O's again. Don't forget about the pairs of electrons that were already paired up to begin with. So they stay where they were. And now I have a circle representing one line and a circle representing another line. So I have a double bond occurring, and the double bonding has to be in between. So that is my final product. Once again, if you want to check your octet, 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen on the left, and 1, 2, 3, 4, 5, 6, 7, 8 for the other. So that is drawing a covalent bond, showing the sharing of electrons. Okay, let's try drawing H2, so 2 hydrogens plus an oxygen, which will yield or produce H2O, water. So remember I told you, the lesser element should always go in the middle. So I'm going to put oxygen in the middle, and then you should try to make it a mirror image. So I'm going to put one H there and one H on the other side. H has 1 dot each. Oxygen has 6 dots, 2 sides with 2 dots, 2 sides with 1 dots. Make sure your placement is easy for the bonding to occur or to be drawn and represented. So once again, the paired electrons can't do anything. They're already happy, but these 2 lonely ones can bond, and these 2 lonely ones can bond. And I'm circling them to show sharing. So I'm going to redraw it now. I'm going to take my oxygen and I'm going to put those pairs back where they were because we didn't touch them, so they have to go back where they were. And now I'm going to have 1 bond, 1 line between oxygen and the right H. And I'm going to have 1 bond between H on the left and oxygen. And now you can check your octet. So I have 2 for this H because 1 line, 2 for this H. And then if I look at oxygen as a whole, I have 1, 2, 3, 4, 5, 6, 7, 8. So this is your final product. You can always do this for Lewis structures too. Okay, CH4. Show the covalent bonding just for this molecule. Well, C is going to go in the middle. Then the H's have to surround it, 1 per side, because there's 4 sides. H has 1 dot, and C has 4 dots, 1 per side. So every side has a dot that it can pair up with. There's a bond, another bond, another bond, another bond. I have not left any dots alone. So if I clean this up, every circle is going to become a line. So now I have a single bond between the left H and C, a single bond between the upper H and C, a single bond between the right H and C, and a single bond between the bottom H and C. Okay? Each H only has one line attached to it, so that's 2 dots for each H, 2 octets, or 2 electrons for the octet. And then the C has 4 lines coming from it. Each line is 2, so 2, 4, 6, 8. So that is drawing covalent bonds. Moving on to ionic bonds. We said ionic bonds transfer electrons. So we're not going to show a circling because they're not shared. We're actually going to use an arrow to show where does the electron move to. And this is really the first time that you are truly representing an ionic bond. So I have K potassium plus F fluorine combining to yield or produce KF, which is potassium fluoride. So I have one of each. So K, and K is in group 1. And then I have F, which is in group 17. And this is an ionic bond. I know that because it's a metal and a non-metal. I also could use my electronegativity difference to determine an ionic bond. And I'm not going to circle these. I'm instead going to show where does the dot go to. So K has 1 to give up, and F needs 1 to accept. So I'm going to draw an arrow from the K electron to the spot on the F. And I'm going to now draw K has no dots. Technically, when an outer shell is emptied, it gets deleted or erased, and the next inward shell is already full because you have to fill from in to out. But we're not going to represent that here. So all I want to know is the charge. So I know that K got rid of 1 electron, but is K's charge going to be positive or negative? Well, it lost 1 electron, so it lost negativity. If you lose negativity, you become more positive. So plus 1 is the charge for K. It is showing that it lost an electron, it gave 1 up. Okay, then I'm going to draw F. And F now has, technically, if you draw it down here, it has 1, 2, 3, 4, 5, 6, 7, 8. And this is the dot that it accepted. So what's the charge going to be on F? I know it accepted 1 electron. It accepted negativity, so it's going to be negative. So I'm not going to actually draw the dots around this. I'm just going to show the charges. If you need to draw this down below, that's fine, but this is going to be my final answer. And these should cancel out. If they don't, you've done something wrong. The positive and the negative make these 2 atoms come closer together, and that's how you get the potassium and the fluorine to bond into potassium fluoride. A little more complicated to think about just because of the charges. Okay, let's try another one. Magnesium will react with 2 iodines, I2, and it will yield MgI2, which is magnesium iodide. So remember, the lesser element is always in the middle, and then I on one side, I on the other side. Magnesium is in group 2, and iodine is in group 17. I once again have a metal and 2 nonmetals, so it's an ionic bond. Whoops, I drew too many there. Make sure you're checking. Don't just start rambling. Okay. Remember, metals always give their electrons. They're always the cations. So magnesium has 2 electrons to give, and iodine each needs 1 electron. The metals are always giving, the nonmetals are always taking. So this electron will be given to this iodine on that side, and this electron will be given to that iodine on the other side. So I would prefer you to write it in this format, but I'm going to just have you do it simplicity for now. So you're just going to rewrite it like this. That's fine for right now. You'll learn why it's this structure in chapter 7. But, okay, this iodine on the left gained an electron, 1. It gained negativity, so its charge will be -1. This iodine also gained an electron. It gained negativity, so it is also -1. Magnesium gave 2 electrons. It lost 2. If it lost electrons, it lost negativity, becoming more positive. So each iodine should be -1, and the magnesium should be a positive 2. And if you add these all up, they equal 0, which is how you get the ionic compound. Just to show you up here, if this is a more sophisticated way of writing it, which you don't really know right now, but it would technically look like this. So still the +2, and then you multiply this to say it's -2 overall with 2 iodines. So that's why this is a little more complex, but you're totally fine to write it like this for now. All right, let's try another one. Draw an ionic structure, because this is not showing a reaction, between beryllium and fluorine. So Be, there's only one, it's going to go in the middle, and 1 fluorine per side. Beryllium is also in group 2, so this should look a little bit familiar. Fluorine is in group 17, 7 valence electrons. Once again, I'm going to show the metal beryllium can give 1, and fluorine needs 1. So this electron will be given, fluorine will take it, ionic bond, give, and a take. And if you need to redraw the new structure below, if that helps you out, if you want to redraw it like this, okay, here's that new electron. Beryllium is technically empty, but its next inner shell is full, I promise. If you want to draw it like this, feel free to show that, yes, the F's are happy, and Be doesn't have anything. I promise you it's happy. Okay, so I'm going to redraw it in the order I give you, or the order I wrote it. So F, Be, and F. This is the same thing. It's just showing the F's combined. The F gained an electron. They gained negativity, so they're -1s. And the beryllium lost electrons. It lost negativity, so it is a +2. Very similar to the last example. So +2 and -1 and -1 equals 0, which is how you get the compound. Okay. The only way this can get more complicated is to first determine the difference in electronegativity, and then determine the bond type by that, and then draw the bonding. So I'm not telling you if it's an ionic or a covalent bond. But remember, ionic bonds are between metals and nonmetals. Covalent bonds are between similar atoms. So you could still potentially kind of look at this and know, or you could just use your electronegativity chart and do what the problem asks you. So looking at my electronegativity chart, I'm only going to look at C and H. I'm not doing anything with the subscripts. You're not going to multiply anything by 2. It's just C versus H. So hydrogen's electronegativity value from the chart is 2.20, and carbon's electronegativity value is 2.56. Okay, so you're going to subtract 2.56 minus 2.20 to find the difference in electronegativity, which is 0.36. And if you look on your chart, 0.36 falls into the nonpolar covalent bond type, and the key word here is covalent. So I know this is going to be a covalent bond. So I'm going to use circles to represent the bonding, and then I'll replace those circles with lines. So I'm going to have H, C, there's another C, C's are in the middle, and another H. So make sure you have everything that you need, 2 C's, 2 H's. Very symmetrical if I cut it in half. Each H has 1 dot, each C has 4. Group 14, 4 valence electrons. So match up the easy ones first. You're drawing to show the sharing. Sharing here, and then between the carbons, it's also going to be a lot of sharing. Now I'm going to replace the the circles and the dots with dashes or lines. So I've got, once again, an H, and there's 1 circle here, so that's 1 bond to the C. I'm going to leave the middle blank for right now. I have this C and 1 bond to an H. And then between the 2 C's, I have 1, 2, 3, triple bond. Check your octet. H has 2, H has 2, C has 2, 4, 6, 8, 4 lines, 2 dots each, and same with the other one. That's all you have to do. No checking of charges because it's covalent. But once again, you first had to use the electronegativity chart to find the values, subtract to find the difference, and use that difference to figure out what type of bond it is. For right now, we're just concerned with covalent. It doesn't matter if it's polar or nonpolar. All right, let's try one more. So once again, determine the difference in electronegativity and the bond type, then draw the correct bond. So I have B boron and F fluorine. Doesn't matter how many, I'm just comparing those two atoms. So B's electronegativity value is 2.02. Make sure you're using the right symbol and the right number. It's going to mess everything up to begin with. F is the highest electronegativity value of 4. So the difference in electronegativity is going to be 2.02, which is equal to an ionic bond. So now I'm going to be using, once again, those arrows to show the bonds occurring, the give and the take. And then I'm just going to rewrite the symbols with the new charges. So I'm going to put my B in the middle, and I'm going to surround it with my Fs. You can put the Fs wherever you want. You can put the other F on the top. You can put this F on the top. It doesn't matter. You should have one side with nothing, 3 sides with an F. So B boron is in group 13. So it has 3 valence electrons. And F is in group 17. Once again, you have a metal boron and a not, well, actually, boron is technically a metalloid, so you can't even use that to determine this. But okay, so I have this happening. So each fluorine needs 1 electron, and boron, whoops, I forgot to finish. Poor fluorine. Each fluorine needs 1 electron. There's 3 of them. They each need 1 electron. Boron can give 3 electrons. So boron's going to give 1 to each fluorine. So I'm going to redraw this. I'm just going to keep it in the same shape. Why not? I'm just trying to see if you get the hang of this. So if you need to redraw the dot structures, that's fine. But each fluorine, I don't know why I keep saying fluorine gained an electron, so they gained negativity. So they're all -1 because they gained negativity. Don't let the word gain make you think of addition. You have to think about what's being gained. And then boron gave away 1, 2, 3 electrons. And it gave them away, so it became less negative and more positive. +3 minus 1, 2, 3 gives you 0, which is how you get the ionic bond. So that is actually, once again, determining the difference in electronegativity using the electronegativity chart numbers to determine bond type, and then using that bond type to correctly represent it. You cannot use circles here because it's ionic. You have to use the arrows. And that is it for chapter 6. So the last couple sections kind of ran together. Make sure if you need help on anything you're asking, or it's going to snowball out of control.